So we learned how to find maximum and minimum values. And in this video, we're going to extend that idea, but we're going to add in the restriction that we're talking about on a closed domain. So in the last video, when we were finding maximum or minimum values, we were just looking for critical points anywhere. When we found them, we classified them with that determinant piece. But here, the addition of a domain is going to cause a little bit of an extra wrinkle. So let's remind ourselves of the extreme value theorem, which we would have saw in single variable calculus, but it works in multivariable as well. So if f is a continuous function on a closed and bounded set in D, so D is its domain, and the D is a set of R2. What does closed mean? Closed means that the boundary of the set is included, so we can get to the edge. Closed and bounded set, so it doesn't shoot off to infinity. Then the function obtains its extreme values, its absolute maximum and its absolute minimum in that closed D domain bounded set type thing. So what does that mean practically for us? Well, we do the same thing that we did last time. We're going to set the first order partials equal to 0 and find the critical points. If that critical point is not inside our bounded domain set, then we don't count it. If it is inside, then we use that big D method to figure out, is it a maximum or a minimum or a saddle point. Then after that, we look on the edge of that closed bounded set, and we check on the edge if there's any extreme points on the edge. Now, we won't catch the extreme points on the edge with our first method of setting the partials equal to 0, because they might not be, both derivatives might not be equal to 0 there, but it's a boundary point, so it could kind of go up to that boundary point and be a maximum. We'll see that in this example. Let's take a look. So here we've got our function, x to the 4, y to the 4, minus xy, but we're on this set then, this square. We're only interested in maximum and minimum values on this closed rectangle. X goes from 0 to 2, y goes from 0 to 3. So I have this function graphed here. So there it is, and we've seen functions like this before. I can see that it's got a minimum, and right in the middle of those two minimums is a saddle point. And this is the sort of graph that we would spin around if we were just saying find and classify the critical points. But I want to restrict to our domain. So let's take a look here. X only goes from 0 to 2. So I don't need to see any x values. I don't want to see any x values that are not outside that 0 to 2. And y values are supposed to go from 0 to 3. So there's our restricted domain on that rectangle. So now take a look. Before we jump into the math, we have one of those minimums that we would have had before, but the other one, the other minimum, we don't include that. It's not in the domain. Now, what do I mean by so we don't even touch that side. I'm gonna have to increase the z a lot actually. So I'm gonna make the z go all the way up to 20. Now I'm gonna make the z go all the way up to 80. Yeah, to where you finally touch it. So we're getting some maximum values here where that curve goes up and touches the side of the box. So we have to check the boundaries then where the curve touches the side of the box. Let's jump back into the math here. First thing to do, we start off in the same fashion as we would have done if there wasn't a closed bounded set. Closed, all of these are less than or equals to greater than or equals to. So we can be on the boundary. So I need our second order partials first. We're finding the critical points, just like before. Take the derivative with respect to x. I'm going to set that equal to 0. Take the derivative with respect to y. We're going to set that equal to 0. So we're setting these first order partials equal to 0 to find the critical points. Now, just like we've seen in the previous video, I can write this as y is equal to, so it's two equations, two unknowns, and I can write this other equation as x equals to, and I'm going to note right off the bat that 0, 0 solves this system of equations. So 0, 0 is a critical point. Oh, wait, it is a critical point I care about if it's in the region. It is in the region. It's actually a corner of this box. So I'm going to make a note of it. It's a critical point that's inside the region. The value is at 0, 0, the value is 0. So let's make note of that as well. So z at 0, 0 is equal to 0. All right, now we can solve these with substitution. So I'm solving these two equations. The first equation is x is equal to 4y cubed. And in for y, I'm putting this 4x cubed. Which gives me the equation x is equal to 4 times 4 cubed, that's 4 to the 5th. Oh wait, this is supposed to be cubed. Yeah. So that's 4 to the 4. And x to the 9. And now I'm going to cancel an x off both sides. I've already taken the x equals 0 into account, so it's okay to cancel the x off both sides. So now this solves as x is equal to the 8th root of 1 over, that's 4 to the 4, which would be like 2 to the 8. So when I take the 8th root of 2 to the 8, that's just going to be a half. So this works out really nicely. But like taking the 8th root's like taking the square root. I got the plus or minus to think about here. So now I've got two other critical points. I've got, if x is equal to positive 1/2, then y is equal to, that's going to be 1 over 8, positive 1/2. So that's one critical point. The other critical point is when x is equal to minus 1/2. Oh wait, that's outside the box. The minus 1/2, minus 1/2. So I'm not counting it. So the 1/2, 1/2 is the critical point that's inside this rectangular domain. And let's get the z value at that. Let's get the z value, the height at that. When I plug a half in, I get a 16th plus a 16th, that's 2/16, that's an 1/8. An 1/8 minus, half times a half is a quarter, an 1/8 minus 2/8 is minus an 1/8. So the y value here, or no, not the y value, the z value, the height is minus an 1/8. Now, since I'm investigating these points on a closed bounded set, I'm getting the actual heights, their actual z values, and that way I can tell what's the max and what's the min by just looking at the actual heights of them. I don't need to use that discriminant in this case if I don't want to. And I don't have to because I won't have to take second derivatives then. So far I've got two critical points. And this one at -8 is lower than this one at 0. Now, I found all the critical points that are critical points that are kind of ignoring this boundary. This 0 would be a saddle point if it wasn't right on the edge. So now I want to check these boundaries here. So let's draw what I have here. I've got 4 walls. So this is from 0, x goes from 0 to 2, and y goes from 0 to 3. This is the wall, x equals 2. This is the wall, y equals 3. This is the wall, x equals 0, and this is the wall, y equals 0. So I've got 4 walls and 4 corners to check. This corner I already checked. It's 0, 0, and at that corner z is equal to 0. Let's check this corner here. That's the corner 2, 0. And at 2, 0, z is equal to, okay, that's going to be 16 minus 0. Z is equal to 16 here. At this corner, that's the point 0, 3. So that's going to be, at that point, z is equal to 0 plus 81 minus 0. So z is equal to 81 at this corner. So z is 0 here, 81 here, 16 here. What about here? That's the point 2, 3. So z is equal to, on that corner, that's going to be 16 plus 81 minus 6. So 10 plus 81, 91. So I've got these are critical points. They're points of interest, let's say. So I've got 4 values, and so far this is the maximum, the biggest one I saw. And so far that minus a half in the middle at a z value of -8 is the smallest one I saw. But I need to check these boundaries then. So let's check. I'm going to start here and go clockwise all the way around. Let's start here on the line y is equal to 0. When y is equal to 0, my function, so on that line, z is equal to x to the 4. Oh, I know what that looks like. Looks like that. So it's going to have its minimum on this side and its maximum on this side. So I already took those two into account. Why wouldn't it have a maximum or minimum on the corners? Well, if for some reason it went up and then like this, then there'd be some critical points to take care of there, but it doesn't do that. So I can erase that. Zip. On the curve, this is the curve on x equals 2. On x equals 2, the function is z is equal to 16 plus y to the 4th minus 2y. Now here, this one I knew the shape. That's a 4 here. But maybe this I'm not so familiar with. So let's take our derivative. And I'm writing z prime because on this wall, I'm only changing y. Now at this point, z is only a function of y. So I take the derivative and I get 4y cubed minus 2. And if I set that equal to 0 to see if there's any peaks or valleys here, I'm getting y cubed is equal to a half. So y equals the cube root of a half. And that's in here. So it is something I have to pay attention to. It's by in here I mean it's between y equals 0 and y equals 3. So this is something that I have to think about. So I need to know what's this is the point 2 and the cube root of 3. And I need to know what that z value is. Okay. If you're thinking as you're watching this video that, man, these questions are a lot more tedious with domains, you're absolutely right. They are. So now what's the z value? I don't want to do that. That's going to be 16. When I cube root that, that's going to be cube root half. Okay. Whatever this is. This looks like it's bigger than this, but not as big as this. So far, this is the maximum, and this minus an eighth in the middle is the minimum. Okay, I check this wall, I check this wall. Let's check this wall. That's the y equals 3 wall. When y is equal to 3, z is equal to x to the 4 plus 81 minus 3x. Same idea here. I'm going to need to take the derivative. That's 4x cubed minus 3. Set that equal to 0. So I get x is equal to the cube root of 3/4, which is in here. So I need to check this point, which is cube root of 3/4, 3. I need a z value for that. Let's get that later to finish up. Last one is the x is equal to 0 wall. And when x is equal to 0, this is just z is equal to y to the 4th. And it's the same as this x is equal to 4th. There's no critical points along here. If I take the derivative and set it equal to 0, I'm just going to get 0. So I've already taken that into account. So what have we got here? It looks like a huge mess, but let's switch to red here and think about our critical points. We found this one, the regular way, setting the two partials equal to 0. And so far that's our smallest value. Then we check the corners. Z is equal to 0, Z is equal to 16, Z is equal to 91, and Z is equal to 81. Then we check the walls, and the walls needed to have a place where the slope was flat in order for there to be a critical point to think about. These walls didn't have that. This one did, and this one did. And we had to figure out the Z values for each one of these walls. We'll see that this sort of dips here along that wall. That's along that wall. So this is a minimum. When I plug this in, I'm going to get a number that's less than 81 and less than 91. Same thing here. This dips here. So I get a number that's less than 16 and less than 81. So these are local minimum, local maximum, global maximum, 91, global minimum, local minimum. Now we've done the whole question. And I guess the only thing left to do then is you'd have to make note. Let's go back. you'd have to make a list of all these critical points then. Notice I didn't classify any of these things by looking at second derivatives. We actually just classified them by finding the heights, finding the z values. And how many critical points? 4 corners, 2 on the edge, so 7. 1, 2, 3, 4, 5, 6, 7. 7 critical points. Local max, local min, global max, global minimum. As we said before, with these boundaries, every time there's a boundary, and even this was a rectangular boundary, it wasn't too bad, we have to check the function specifically on those. So it turns into, one problem turns into multi little small problems. Let's look at another example. This next example, I've tried to simplify it a bit by making the boundary a circle. So x squared plus y squared less than or equal to 4, we have to be inside that circle. Now how is this easier? There's no corners to check because it's a circle, and there's only one boundary. So whereas the square had 4 sides and 4 corners to check, the rectangle from the last example, this will have no corners and only one boundary. But we go through the procedure in the same fashion. So this should be a little bit easier. Let's find our critical points ignoring the boundary. So I've got 4x cubed equals 0. So x, that's going to be an x equal to 0. But I need the other one too, right? 2 equations, 2 unknowns. So z sub y is equal to 2y minus 1. And if I set that equal to 0, I get one critical point, which is 0, 1/2. Okay, do I keep this? Yes, if it's in the circle, no, if it's not. It is in the circle, so I do keep this. So I need to know what the z value is at this point. That's going to be 0, 1/2, that's going to be 1/4 minus 1/2, minus 1/4. So I've got one critical point and I know its value. Now I need to check the boundaries of that circle. So on that circle, x squared plus y squared is equal to 4. So on the circle, I need to substitute in here. I could solve either for x or for y. I'm going to choose to solve, because of the way the algebra looks, I'm going to solve for x squared. Because there's only an x to the 4th here, and if I solve, that'll be x squared squared. I don't have to worry about the plus minus and the square root. So on the boundary, x squared is equal to 4 minus y squared. So the z function is equal to z squared squared minus y squared plus, or minus, no, plus y squared minus y. Okay, so now z is only a function of y. That's on the circle. So now it's are there max and min there? It's going to be take the derivative, set it equal to 0, solve. Let's expand this out, because I think it'll just make our derivative taking easier. Yeah, because now if I go z prime, I get 4y cubed minus 14y minus 1. Now that I'm going to set equal to 0 and solve for y. Now, sure. The problem with this, though, is that this doesn't factor nicely. There is a cubic equation just like there is a quadratic equation. I'm going to do this numerically. So I'm going to solve for y, but I'm going to ask for just numeric answers to make the problem go smoother. And any xy point that's outside of this circle, So in other words, if you give me a y that's bigger than 2 or smaller than -2, I'm going to throw them out. They're all in between plus or -2, so they all count as critical points. So that's going to mean I get 3 critical points, or maybe even more. Let's see here. Let's talk about the critical. Let's start with this one. Why do I say 3 critical points? Because x is equal to, I'm going to go back up to here. X is equal to plus or minus the square root of 4 minus y squared. So each one of these y values is giving me 2 x values. So first critical point is with this almost 0 y value. Second critical point is with this y value. And third critical point that I found on the boundary and I should get two x values here. So it's going to be plus or minus this value squared. I'm going to get plus or minus that y value squared plus or minus that y value squared. So let's put those y values in. Put the bracket in there because I want the machine to see the minus. Now, okay. Let's get a number for this. So this is 2 critical points because it's plus minus for that. Let's get a number for this. That's 2 critical points. So we found one in the middle, one critical point in the middle, and we found 6 along the outside, 6 along that circular boundary. Okay, now we need to figure out the z value for each one of these 6 critical points, and then we'll think about them being maximum or minimum. Before we jump in and do that, I'm looking at this function here. This is z around the outside of that circle. Just out of curiosity, let's see what it looks like. I'm just going to ask for a picture of that. And okay, it gives me a picture, but I only want to see from -2 to 2 because that's the only y's that we could actually have. Oh, so I see there's those critical points here, here, and here, right at the edge. That's near the one that's near 0. So I'm seeing these critical points that we found, but each one of these is giving me a plus or a minus x value. Okay, Just curious as to see what that looks like. So now we need to get the z values at each one of these points. Before we do that, again, because I would like to see pictures rather than, we're just going to get the z values, and we're going to pick the biggest z value to be the maximum and the smallest z value to be the minimum, and then we're going to go through all 7 of our z values, 1, 2, 3, 4, 5, 6, 7, and decide which one's the biggest and call that the global on the domain maximum, and which one's the smallest and call that the global minimum. That's what we're doing. So all that's left for me to do is get those values. But let's go back to our picture here. This is x to the 4. Let's see. Okay. X to the 4 squared minus y. And I don't want to go all the way up to 80. So here's our function. And I can see now this is unrestrained, and I can see that minimum at the bottom, that minus a half. Let's put that circular boundary in and see what we can see. That circular boundary, x squared plus y squared is equal to 4. Now we got to be inside that tube. So when we're inside the tube, we're kind of on the boundary where, so here I'm looking up, we haven't intersected the tube yet on these sides. But we do have some intersection points. This curve here, there's a minimum on that side, will be a local minimum. There'll be a local minimum on this side. As we go all the way up, there's got to be a maximum. We haven't reached it yet because it hasn't intersected this circle yet on this side and this side. Okay. So I see a maximum here. Minimums, maximums. I'm looking for the intersection of those two curves. Can I make this one less than or equals to? Yeah, so I want to be in, just to make it all one color so I could see it. It's a lot easier to see. Yeah, minimums. Looks like there's going to be one here on the corner and then all the way up to where it crosses over. Yeah, anyway, wanted to see the picture. What's left to do? And we left this busy work here, finding the values. Let's do 1, and then the rest we can leave for later. So I want to know what's the z at, let's take this point here with the positive. Well, that's just taking our function this x value. Now plus or minus, because it's to the power of 4, doesn't matter. And let's just evaluate this. So I've got a value here. So here I've worked out the heights, the z values at each one of those 6 critical points. So we've got our global maximum on that circle at 16, and the global minimum happens inside the circle at -1/4. All right, so circle was supposed to make it easier, but the numbers were decimally weird looking. Let's see if we can try one more that's kind of a balance between the two. So I've got myself a triangle here as far as let's draw our region. So our triangle, x and y have to be positive, and here's our x plus 2y, which means the biggest y could ever be is 4, and the biggest x could ever be is 8. So we have this triangle here. And that's the line, I guess we could make it the line y equals, but it's easier to make it x equals, just the way it is. So x is equal to 8 minus 2y on that line. This is the line y is equal to 0, and that's the line x is equal to 0, and we've got it's a triangle, so there's 3 corners. There's 0, 0, there's 0, 4, and there's 8, 0. So there's 3 boundaries and 3 corners to check. So let's get our z values at, let's get at z at 0, 0, because that's easy. Zip, that's 0. Let's get our z value at 0, 4. So if x is equal to 0 and y is equal to 4, so this is going to be minus 32 plus, what's that, 16 times 16, 256. All right, well, got to write this in here first. The other one's going to be at 8, 0. So we've got 224, and if I plug in 8, 0, that's going to be 24 minus 512, 0, 0. So that's going to be minus 448. So we've got all the corners worked out. Now let's take a look at the boundaries. On the boundary x is equal to 0, so on x is equal to 0, our z is minus 2y squared plus y to the 4th. We take our derivative, so I'm on this boundary here. Take the derivative, so that's going to be minus 4y plus 4y cubed. When I set this equal to 0, I can factor out a 4y, and that's going to be minus 1 plus y squared. So either y is equal to 0, and I have that, or y is equal to plus or minus 1. Minus 1's not in our domain, so y is equal to 1 is our only critical point on here. On here, because I made x is equal to 0. So here's this critical point, and let's put our next one in here. That's the point 0, 1. So z at 0, 1 is equal to 0, 0 minus 2 plus minus 1. That's this boundary. Let's check this boundary where y is equal to 0. So we'll change black pen here. When y is equal to 0, our curve is z is equal to 3x minus x cubed, We're going to take the derivative of that, so that's 3 minus 3x squared. When we set that equal to 0, I get x is equal to plus or minus 1. Minus 1 doesn't count, so x is equal to 1 is the only one. So that's z at 1, 0, and that's going to be 3 minus 1, that's going to be 2, 0, 0. That's here. Oh, we had that other one. I'll just keep it at here. Last thing we got to do, well, we never checked the interior. We never took the derivatives here. Let's check this one, 8 minus 2y. Let's go back to the other piece here. So, to finish up what we're doing, we're on the boundary where x is equal to 8 minus 2y. And so, on that, everywhere there's an x, I'm going to put an 8 minus 2y. Everywhere there's an x, I'm going to put in 8 minus 2y. All right, so here's our function. Let's expand this out to make it look a little bit easier to take the derivative of. It's just a great big polynomial. I want you to go in here. All right, I know what the deal was with that. Z prime, 4y cubed plus 3y squared minus 52y plus 186. I'm setting that equal to 0, the derivative equal to 0. Another cubic. I'm not going to worry about factoring it. Let's just solve it numerically. We get, two complex numbers, throw those out, and a y that's not in the, so there is no solution to it that's in our interval. So back here, this wall has no critical points. So the only thing we got to do now is we got to see if there's any interior critical points. When we set the two partials derivatives equal to 0, is there anything inside that triangle that's a dip or a hill? All right. So I need the two first order partials here. So z sub x is equal to, that's going to be 3 minus 3x squared. And when I set that equal to 0, I get plus or minus 1. So minus 1 doesn't count because it's not in the triangle. So x is equal to 1 is our only option. Y is equal to, or y sub, z sub y, taking the derivative with respect to y. 0, 0, that's going to be minus 4y plus 4y cubed. I set that equal to 0, and I get either y is equal to 0 or y is equal to plus or minus 1. So the minus 1 doesn't count, so we get y is equal to 0 or 1. So here I get two interior critical points. 1, 0, which we actually already had because that's on the boundary. So I'm not gonna worry about that one. And 1, 1. The 1, 0, we already had that one. All right, so I just need the z value at 1, 1. That's going to be 3. That's going to be 2, 0, 1. So z equals 1 here. So I'm going to go back. We found a 1, 1 critical point right here. and z at 1, 1 was equal to 1. All right, global maximum, that's the biggest value we found, 224 at 0, 4. This is the maximum. And global minimum. All the other ones are local max and local min. This 2 would be a local max because we've got here, this has a value, sorry, this 1, and this one's a 1, 0. This one's a 2. So it goes up. It would be a global minimum here. And this way it goes down to -1. Oh, so this is neither a max nor a min here. This would probably turn out to be a saddle point if we did our second derivatives. Optimizing on a closed region. Okay, a couple of little pitfalls. Let's point out what's going on here. What if our region's not closed? Okay, what if our region's not closed? If our region's not closed, I'll just draw it over here. If our region's not closed, let's say this boundary was dotted, if for some kind of weird problem, then I don't check this boundary because I can never get there. So this boundary doesn't count. The theorem has that it achieves its extreme value, its maximum, its minimum, on a closed bounded set. So the extreme value theorem doesn't count on this, but mechanically we don't check this boundary. It does seem like having a boundary makes these max-min problems a lot more trouble. Yes, but they're a lot more realistic.